Alright, let's do a quick update on the linear regression. All I want to do very quickly is show you a little trick with regards to determining the goodness of fit. And what I've done here on this data that we have right here, these are the same data that we did the linear regression for. So these are the weights of the red-tailed boa against time. I've produced the plot, the original plot that we had in class, that is the regression line with the confidence bands around it. And we'll look at that again in a minute. What I've done here is added one additional statement, and that is plot paren boa model. So I've looked at my boa model up here. There's my ggplot2. We talked about how to get that loaded into the system. That's all in there. Now all I'm doing is plotting the results of that linear model. And when you do that, the first plot that shows up is this nice plot here of the residuals. So you see this dashed line right at the zero. That is essentially your regression line laid over on its side. And these then are the data points around that regression line, and then what R has done is drawn a little line through there to show you basically what the weighting of those points is around that regression line. Not officially a weighting, but it's just basically fitting this crude little line through the center of those points. And the first thing that you'll notice is that those points are not distributed equally around that horizontal line, around that regression line that is now laid on its side. So you know that something else is going on with the data. It's probable that a linear model is not perhaps the best model to fit these data. Something is going on. The next thing that we can do is look at the QQ plot. So this is a plot of quantiles of the normal distribution against quantiles for our standardized residuals, so for what's happening with our observed values. And this dashed line here is the line of isometry. And if the data are perfectly normally distributed, then what you would get is that all of these standardized residuals would fall exactly on that line of isometry. So the x-axis is the normal distribution, and the y-axis is essentially our observed distribution. And you can see that the slope of our observed values is somewhat flatter than what's happening in the normal distribution. And what that indicates is that we don't have a good match between those two distributions. It turns out that that relative to the normal distribution, our observed distribution is a bit leptokurtic, so it's skewed off at the ends. The next plot that we can look at is sort of the fitted values on the x-axis and then the standardized residuals. That's basically just another way of looking at our plot of residuals that we saw in the first graph. And then there is another graph here which is plotting Cook's distance, indicated by this red line here. And that's essentially just another way of looking at these residuals. Cook's distance is sort of an interesting metric to try and explore what the deviation of your observed points is from the expected. And it uses a sort of leverage statistic in here. If we have time, we'll talk about that in class. The two graphs that we really care about are this QQ plot and then the plot of residuals. And we'll talk a little bit more about this in class. And then obviously the plot that we produced last time is this plot. Our observed values. The red line is our predicted, is our regression line. And then the blue are the 95% confidence intervals for that regression line. Not for the points, but for the regression line. All right, see you guys in class. That's it. Bye.